Good afternoon, everybody. Hope you're all healthy and safe. We are going to continue with our chapter 6 on self-adjoint operators. Today we'll be discussing Theorem 6.2.3, and this is also called as the Hilbert-Schmidt theorem. So this theorem is basically, it consists of, there are two more parts for this theorem. So in order to the length of the theorem is a bit long, so I'll be discussing it in 2 lectures. So in this lecture we shall be just proving the first portion, and in the next lecture we shall be discussing the other remaining portion of this particular theorem. So let's move on to the Hilbert-Schmidt theorem. It's the first Hilbert-Schmidt theorem. That is, for every non-zero compact symmetric operator, there exists a set of non-zero eigenvalues such that modulus of lambda 1 is greater than equal to modulus lambda 2 is greater than equal to, etc. Okay, and this sequence or this set is either it is finite or it will be converging to 0. So this is what we have to prove. That is, for any non-zero compact symmetric operator or compact self-adjoint operator, there always exists a set of non-zero eigenvalues which satisfy this condition. That is, modulus of lambda 1 is greater than equal to modulus of lambda 2 greater than equal to, and so on. Okay, and this set is either finite or converging to 0. So this is the first portion of our Hilbert-Schmidt operator. So we shall be going on to the proof of this. So it is clear we'll be using the method of induction. So that is, we shall find a set of eigenvalues, and once we can get the eigenvalues, we can find a corresponding set of eigenvectors also, right? Eigenvalues lambda I and the corresponding eigenvectors. Let me just write it out. Corresponding eigenvectors inductively. Okay, so we are going to apply the process of induction. So first, T is given to be symmetric or self-adjoint. Okay, as T is symmetric and compact, just recall the property 6.2.1. By property 6.2.1, there exists a lambda 1 such that modulus of lambda 1 is equal to norm of T. This is what we had just proved, and an eigenvector corresponding to this lambda 1 with the property. What is property of this eigenvector? It is that norm of E1 is equal to 1, and since it is eigenvector, T of E1 is equal to lambda 1 E1. Okay, so as T is symmetric and compact, by this property we can always find an eigenvalue such that modulus of lambda 1 is equal to norm T, and E1, an eigenvector T of E1 is equal to lambda 1 E1 with norm of E1 is equal to 1. This was our property 6.2.1. So I have stated that we will be using induction method. So for I is equal to 1, the result is true by property 6.2.1, right? So now we shall introduce the induction hypothesis. That is, suppose the set of eigenvalues, suppose set lambda I is equal to 1 to n, and set EI, that is the corresponding eigenvectors 1, is already defined. Okay, suppose that this set is already defined, and the property is by inductive process. That is just explaining, and that is T of EI is equal to lambda I EI, and norm of EI is equal to 1, and also modulus lambda 1 is greater than equal to modulus lambda 2, etc., greater than equal to modulus lambda. And suppose this much is with us, that is the result is true for I is equal to 1 to n. So we have to prove for I is equal to, we have to prove for I is equal to n plus 1, right? That is our inductive hypothesis. So what we are going to do is we are going to consider, let En equal to the span of set of eigenvectors I equal to 1, 2. Okay, let En be the span of the set. Then we can say that T of Ei is equal to lambda I Ei, right? So T, whenever acting on any element of this span, it gives us a combination of, again, this element itself, combination of eigenvectors itself, right? So T of so that is, if I am writing T of E1 plus E2, what do I get? I get T of E1 plus T of E2, that is again lambda 1 of E1 plus lambda 2 of E2, right? So this is actually, I am getting again an element of the span of Ei only. So I am just saying this because I am going to say that T of En is contained in En. Okay, then T of En is contained in En, and hence I can say En is an invariant subspace. It is an invariant subspace of T. Okay, and by property 6.1.3, En, if En is an invariant subspace, then En orthogonal is also an invariant subspace. Is also an invariant subspace. Okay, so we have got an invariant subspace of T. Now I'm going to, for a bit easier notation, I'm going to denote Tn plus 1 to be T restricted to En orthogonal. Okay, that is Tn plus 1 is nothing but T is restricted to En orthogonal. So T is symmetric. T is symmetric, it is given to us, and it will be symmetric, it will remain symmetric over any subspace of invariant subspace of T. Okay, T is symmetric and it will remain symmetric. It will remain symmetric over any subspace, okay, which is invariant subspace. So I can say that T restricted to En plus En orthogonal is also it is also symmetric. So from this property I can say Tn plus 1 is also symmetric. So again we have a symmetric operator with us. So by the property 6.2.1, what can I say? We can get an eigenvector En plus 1 such that norm of En plus 1 is equal to 1 and T of En plus 1 is equal to lambda n plus 1 into En plus 1 and mod lambda n plus 1 is equal to norm of Tn plus 1. So this is all obtained from the property 6.2.1. Okay, so we have obtained an eigenvector for I is equal to n plus 1. Now we just need to show that whether it will be greater than or equal to or not. That is, the inequality must be satisfied. So now we have En is En minus 1 is contained in En. That is clear by the definition. Okay, and this implies we get En orthogonal will be contained in, that is, we have seen this earlier also, when we are talking about orthogonal set, the inequality or the subset condition will be reversed. Okay, so E of what did I say, En orthogonal is contained in En minus 1 orthogonal. So this implies T of En orthogonal will be contained in T of En minus 1 orthogonal, because we have seen that it is a invariant subspace. Now let's see whether the inequality is satisfied. What is modulus of lambda n plus 1? We have just now seen that by property it is nothing but norm of Tn plus 1, and Tn plus 1 we had denoted it by T of restricted on En orthogonal, right? T restricted to En orthogonal. So T of En orthogonal is contained in T of En minus 1 orthogonal. So I can say that this norm will be less than equal to T restricted to En minus 1 orthogonal. Then again by the notation I can replace this by norm of T restricted to, or T restricted to En minus 1 can be written as, it is or En minus 1 orthogonal can be replaced by norm of Tnc. That is Tn plus 1 was considered to be T restricted to En orthogonal. So when you are considering, instead of En we are considering n minus 1, what will happen here? It will become T n minus 1 plus 1, that is Tn. Okay, so I hope this is clear. And by the property again, norm of Tn is nothing but norm of lambda n. So we get modulus lambda n plus 1 is less than or equal to modulus lambda n. That was the result that we wanted to prove. So we have proved that by induction method such a set of eigenvalues and the corresponding eigenvectors exist which satisfy the following inequality. Now this will stop when the set of eigenvalues for a corresponding operator T is infinite. Okay, I'll just note it down for you, because you're considering the set to be finite. So the process stops when two cases. First one, the operator T is, or Tn plus 1, that the corresponding operator is 0. If it becomes 0, then we cannot find the corresponding set of eigenvalues. And the second case is when the set of eigenvalues is infinite. Okay, these are the two cases when this induction process will stop. So that was about the Hilbert-Schmidt theorem, the first portion. That is, just like I've stated, this is just the first portion. The remaining two portions will be discussed in the next class. So just go through these things in mind and just look into the theorem once again. So that's it for today's session. Thank you.